So e to the a is defined by the power series of the matrix, right? I'm going to put this away and work through it for you guys, if you don't mind. There's no way I could write as many examples as I just showed you, right? But it's kind of important for you to get a sense of what's out there to understand the problem. The problem is, in a nutshell, we don't have enough solutions with just eigenvectors, right? They get us a lot of it, but just not quite all of it. The matrix exponential gets us the rest. I don't think the matrix exponential is entirely explained in the text, and that's unfortunate. Text is usually pretty good, but I think some of the matrix exponential stuff has been relegated to exercises. Don't worry, I'll give you a pretty complete exposition here. So, fortunately, this is the start of class, so you're all fresh and ready to learn new things. It's good. Perfect timing. Hardest thing today. Well, I don't know. Parts of this are hard. Parts of this not so much. So e to the, let's say, b is I plus b plus 1/2 b squared, 1 over 3 factorial b cubed, and so forth and so on. This is the series for the exponential, just feeding it a matrix. So if I do e to the ta into the matrix exponential, that's I plus ta plus 1/2 t squared a squared plus 1 over 3 factorial t cubed b cubed, a cubed rather, and so forth. The reason for that, of course, is that if we take ta and we raise it to the k power, that's just going to be t to the k, a to the k. That's just sort of basic matrix math, right? So like, if you take a scalar multiple of a matrix, there's this law of algebra. We can just take the scalar raised to the same power, the matrix power. All right. So, what observations can we make about this? Number one, if we take e to the 0 matrix, what does it give us? So if I, what's that? No. This is the identity matrix here that we've seen a couple times today. It just gives us the identity matrix. Everything else is going to be 0, right? Like it's I plus 0 plus 0 plus 0 plus 0 plus 0 plus 0. We could be here all day. So just the identity matrix. E to the 0 is I. I is like the number 1. This is a good sign. Just like e to the 0 is 1, right? E to the 0 matrix is the 1 for matrices, the identity matrix. 2, and this is not entirely obvious, a short calculation shows if AB is equal to BA, then e to the A times e to the B is, guess what? E to the A plus B. To quote a certain ninja, believe it. All right. So point number 3 is if we have TA and we have like minus TA, that's equal to minus t squared a squared, which is also equal to, by the way, minus TA times TA, right? So my point here is that TA and minus TA, these are matrices which commute. A matrix commutes with a scalar multiple of itself. This is true. And so e to the TA times e to the minus TA is equal to the TA minus TA aka e to the 0, aka I. So what I'm really trying to get at here is that, and this is really nice, is that e to the ta inverse exists, and it is in fact just e to the minus ta. That's what that calculation shows. For which matrices? Which choice of A is this true? Any. I haven't proved it for you, but it can be shown that this series converges for any matrix. The factorials are very forgiving. They make things get small. So any matrix, doesn't matter how big it is, this series will converge. In fact, absolutely. So the matrix exponential is an invertible matrix. And its inverse is this. But more to the point, we also know that the determinant of e to the ta is not equal to 0 then, because its inverse exists, right? I cannot help but misbehave and tell you things. So the determinant of e to the ta is actually the exponential of the trace of a, by the way. The trace of a is the sum of its diagonals. So like there's more that's known. In fact, we also know that the determinant actually is the exponential of the trace of the matrix. There's also a formula that's a generalization for part 2. Like if a and b don't commute, more generally it's true that e to the a times e to the b is equal to e to the a plus b plus 1/2 the commutator of a and b plus stuff. So to know how matrices commute is what you need in order to multiply their exponentials. What I just wrote in red is just for your informational purposes. You can ignore it if you want, but these formulas are really important to quantum mechanics and like further physics and stuff. So anyway. Okay, so summary so far. The matrix exponential is itself a matrix. It is an invertible matrix, right? So what's the next thing you want to do? Well, this is, after all, a calculus course, right? What calculus are we in? This is calculus 4. Who's counting? It's calculus 6. I think we have calculus 1, 2, 3. I think this is calculus 4. I think calculus 5 would be, for me, I feel like calculus 5 would be complex analysis maybe. And then advanced calculus maybe is calculus 6. It depends on the ordering. I mean, I don't know. At some point you lose track. All right, so check this out. What happens if we differentiate with respect to time e to the ta? So the identity matrix just differentiates to 0, right? This differentiates to what? Just a, right? This differentiates to what? 2 over 2 t, right? That differentiates to ta squared. Then we get what? Plus 3t squared over 3 times 2 times 1. That's 3 factorial, right? Let's see here. So I can rewrite that as a times I plus ta plus the 3's cancel. I got 1/2 t squared a squared because I factored out the a. What's that? it's the same thing we started with. That's e to the ta again, right? So we have a e to the ta. So we have dx dt equals to ax for x equal to e to the ta, right? And the determinant of e to the ta is not equal to 0. What does this say about the matrix exponential then? We've proved the following theorem. The matrix exponential, e to the ta, is a fundamental solution matrix. That means it has all the solutions we need in it. So that second path I talked about at the start of today, it's actually very profitable. So you mean, I mean, this is entirely general. It's kind of sobering. You asked me to solve dv dt equals to av for arbitrary real matrices A. I can tell you the answer. It's e to the ta times a constant vector. That is the general solution. So like v equals to e to the ta times constant vector. That is, in fact, general solution of, although I think I'm hiding some things under the rug here in terms of how the complex solution works out and stuff. I mean, it's true, but at the same time, it's kind of useless. Because what is the matrix exponential? It's kind of hard to calculate, right? I mean, it's an infinite series of matrices. Can we calculate that? I can calculate it for certain matrices. Let me show you one. So this is a special example. What example were we to? 7. So here, if I have A equals to 3, 1, 0, 0, 3, 1, 0, 0, 3. Oh, we have 5 minutes of class time left. Let me make this 2 by 2. Sorry, this is my, all right, I worked too hard. So there's something called the Cayley-Hamilton Theorem. The Cayley-Hamilton Theorem says A solves its characteristic equation. Let me put that into practice for this A. So what's the characteristic equation for this? So we have lambda squared, lambda minus 3i, that stink. Fine. Lambda squared plus, goodness gracious, I can't do math, minus 6 lambda plus 9 equals to 0. The Cayley-Hamilton theorem says that if you look at the corresponding equation for matrices, in other words, if you look at a squared minus 6a plus 9 times the identity matrix, that's going to be equal to 0. That's actually not as useful to me. In the interest of not making this into a 20-minute example, I'm going to be a little bit sneaky, and I'm going to instead notice that, so if you look at it, a minus 3i squared, what's a minus 3i? It's just 0, 1, 0, 0, right? And if you square this matrix, you get back to 0 matrix. Well, the reason I knew that really is the Cayley-Hamilton theorem. So if I look at e to the ta, right, that's a pain. But if I add 0 in a sneaky way, so I do ta minus 3i plus 3i, like so, then that gives me e to the 3it times e to the t times a minus 3i So if you work this out, that first one just gives you e to the 3t times the identity matrix as it happens. And this one here, we can write it out. This is the identity matrix plus t times 0, 1, 0, 0 plus 1/2 t squared, 0, 1, 0, 0 squared, and so forth. But I don't really need to write anything more because already I wrote something which is 0. Like this is 0. Yeah. So just to wrap it up here, I have e to the 3t times 1, 0, 0, 1 plus 0t, 0, 0, which I can rewrite as e to the 3t times 1t, 0, 1. There you go. That's e to the t times 3, 1, 0, 3. And by the way, if we have, dx dt equal to ax has x equal to c1 e to the 3t 1, 0 plus c2 e to the 3t times t1, that would be the general solution. The reason I know that is we have just shown that the matrix exponential is a fundamental solution matrix, which means that every column in the matrix exponential is a solution to the system. So the first column to the matrix exponential is e to the 3t times 1, 0. The second column in the matrix exponential is e to the 3t times t1. If we went through the eigenvector technique would have found for us this piece, right? Eigenvector solution, or eigensolution if you like. But this over here, new. That's the piece we're missing from the other way of thinking. And you see what I mean? You don't just multiply by t. See that? It's not just the first thing multiplied by t, is it? The t is in the first component, but not the second component. The way the t appears is subtle and requires calculation. So I don't know. So next time, this is a special example, right? It's a pretty special example. Next time I'll show you actually how we calculate the matrix exponential. And Hopefully I'm not behind. I need to look at my schedule. When do I give you guys the next quiz? Guys remember? Quiz 2 posted, when is it? Thursday? What's today? Tuesday.